There we go. So hopefully y'all can see it fine. And I'm doing fine, Catherine. Hope I'm doing fine as well. Glad you're here. And the topic today will be the Earth's tilt. So I've been actually planning on uh, focusing my streams more on physics, astronomy, mathematics, um, and discussing these things in more detail. Uh, since the derp is those who are deep in dirt, I don't think they're gonna change. But those who are interested in some science and physics and math and astronomy, uh, I think there's some good interest in talking about the particulars of how these things work. And so I want to focus on that. So I was actually thinking about a question or topic to begin with. And one of my recent subscribers made a little post on the community uh, thread that we have and asked that I talk about the Earth's tilt. So that's what I'll go ahead and talk about today. And what I'll do is I'll follow up with another uh, uh, thread that I'll make of that. And let me see where I can put that at. So you'll see a thread in my community. You can make another thread there as well. And let me know what I'm interested in is any topics you want me to discuss as far as astronomy, mathematics, how they relate. It could be a specific question like how does this aspect of the solar system work, or how does this aspect of stars work, or something like that. It could be solving a type of problem, a physics problem or a math problem or something. Wouldn't mind doing that as well. So, for instance, I'll make a post right now uh, uh, in the community threads. If you go to my channel, YouTube, at darrylberrjr.com, DARRYLEBERRYGR.com, and I'll say what topic in astronomy, physics, or math you'd like me to discuss next. Question or comment. And keep in mind that you can also join Discord, ask questions live. You could also ask in the live chat. But just in case, I'll put the Discord link in the live chat there on this video. So anybody can join at any time. Of course, not necessary to join to partake. Uh, if you'd like to, I'll put the link there. And I think I have my header for one of my other channels there, but feel free to join. So I actually have a channel where I talk about A Course in Miracles. That's the one that's there, the next density one, and other things as well. But that's mostly what I've been talking about there. Uh, I have one where I talk more about science. That's a more advanced channel where I'm literally like reading the books and things that I do in my college classes. So it's more specific and less general. So I'm not sure how many people will find those entertaining unless you're like taking a college course right now. And like I'll be doing like quantum mechanics, classical dynamics, and classical electrodynamics, which I mean, generally, unless you've taken a few college classes in physics and math, classical electrodynamics, just if I talk about it'll not be an intro level. But if you're interested in hearing about it, it's still a good channel, and I hope you all still subscribe there as well. In this channel, I'll speak more on the general level. I'll focus more on like science, astronomy, physics from the more general level, where I would say more of a undergraduate level rather than like a upper graduate level, or the lower undergraduate level rather than the upper graduate level, upper undergraduate level or graduate level. So like the STEM channel will be more upper graduate level, upper undergraduate and graduate level. And this channel will be more undergraduate level physics, entry level physics and astronomy and so forth. And I'm glad you love science, astronomy, math, and physics, Catherine. So there'll be a lot more of that. And I know there's people who like some of the derp as well. So sure, I'll still talk about it once in a while, but more far and few in between as I spend more time actually doing what I enjoy, which is physics and science. So it really got me into the talking about the flat earth derp stuff anyway was, like in my presentation in my recent debate, I presented some of my research I've been doing and talked about stuff that I learned in one of my actual textbooks from class. So I dovetail it into what I'm doing, but I'm actually go more directed to that more often. And Catherine says, biological sciences degree specializing in psychology. So my physics and math is only higher level, and I don't know much astronomy. Well, this channel is perfect for you then. So we'll be talking about some intro astronomy, which is the topic for today, Earth's tilt. So one of the things that's interesting about the solar system, different planets have different uh, axial tilts. Like for instance, I believe is Uranus is tilted almost on the side. One of them is either Uranus or Neptune, one of the two. But let's say this is the planet, and its tilt is more like this. So the axis is sort of this way, and the other axis will be coming around the end. So one of the later planets, Uranus, I believe is Uranus or Neptune, one of the two. But Earth is a little bit different. Uranus, thanks, Larry. Awesome. So Uranus is tilted like that, and I can imagine the seasons must be pretty different. One thing I'll mention, by the way, uh, as a backdrop to our topic about the tilt of the planet, the first thing we can talk about is actually the rotation of the solar system. One of the interesting things that we can do now with our more advanced satellites and telescopes is that we can see the formations of solar systems take place. So, for instance, there's something that we call a protoplanetary disk. We actually have pictures of it now. So I'll actually bring up one of the images. I'll be pulling up some images from one of my textbooks, and this is one from the ALMA array. It's called. So let me share that, and then we'll dovetail this into looking at what the tilt is, how we know we have a tilt to the planet. So if we look at this, this is actually an image of a protoplanetary disk taken by the ALMA array. The ALMA array is like a group of several telescopes operate together as one. So basically, the idea is to go back to the pad briefly. The idea is that the resolution that we can get from a device, just like how this microphone, I have a new microphone, it has a bigger uh, um, receiver, so I probably sound more clear. So basically, if you take, let's say, a cell phone, right, and try to take a picture of something very far away, you have a very small aperture, which is why Veritas flat earthers try to take pictures of stars with a cell phone and they get some kind of blob or whatever. It's not the right instrument. You get you a telescope that has a aperture that's, for instance, my telescope, my night telescope, the aperture is, I believe, 8 uh, uh, centimeters. Is it 8 centimeters, something like that? Probably more. I don't remember the exact one, but it's pretty big compared to a cell phone one, right? It's wide as my computer monitor, the base. I don't even think in inches. I haven't used it in a while either. I've been studying the sun a lot. But what we can do is we can actually get a group of satellites and use them all together in unison so that the effective aperture of our telescope is the breadth of all of these satellites together. That's what the ALMA does. So it's able to look a lot farther away into the sky and take pictures like this of things that's so far into the distance that we're looking into the past, because light takes some time to travel to us. So if I look at something a light year away, then I'm looking at something a year into the past, how it was a year ago. If I'm looking at something, thousands of light years away, I'm looking at something how it was thousands of years ago, because it took thousands of years for that light to travel to us. So what this image is here, we're actually looking into the past at a solar system that's far enough away where the light from its formation is just reaching us, right? So when we look at the center there, the center is a star, and it is awesome, right, Catherine? This is amazing stuff. This is the type of data we can get with the advanced technology we have. So if you could think back to Tycho Brahe, he looked at the sky and made these highly accurate. He must have had really good vision, highly accurate, mappings of the 6 planets that we can see. And then Kepler came along and used that data to come up with Kepler's laws. P squared equals AQ, which we can now plot the planets pretty accurately with. And now we can see planets that they couldn't see because we can use telescopes, right? Now we have these telescopes where we can see the formations of solar systems. So that there's the sun in the middle, and each of those rings on the outside, those are what become planets. So basically what happened is there's these, you could even see it in the image. It's not like a perfectly smooth uh, uh, ring. So what happens is the little clumps, they start to clump more together under gravity, and they start to clump more together. And each of those rings, all the matter in that ring is either cleared out until there's greatly increasing clump, or it's blown away by the radiation of the sun, and then you end up having planets, right? So our solar system at one point looked like that, right? And now what we have is we have this. And actually we could actually still stay in the textbook actually. I can go to one of the images I was going to show from there right now. Let's already have it all set properly. So this is an image. So the image I just showed, that was our solar system, many, many years ago while it was forming. And Earth is the matter in one of those rings. It clumped together and clumped together. Now, the cloud that protoplanetary disk forms from, it has a rotation. Everything has a rotation. And so when those rings clump together into planets, it keeps its rotation, right? Its overall rotation is its revolution around the sun, but yet that clump of that ring of gas was spinning, and as it clumps together, the ring itself has a rotation, and that becomes the rotation of the planet. So when we look at the rotation of the Earth, the rotation is basically a conservation of angular momentum, ultimately from the rotation of the original gas cloud that formed that protoplanetary disk. Then the angular momentum of the disk itself that becomes the angular momentum of the planet, both in its revolution and in that clump coming together. And just like how if you ever look at an ice skater, for instance, and if they're spinning, they have their arms out and they spin more slowly, right? And when they retract their arms, they start to spin really fast. And of course, they make a show out of that where they go around in a circle and their arms are out and they pull their arms and start spinning faster and faster and faster. It looks pretty cool. That's exactly what the planet did, right? So you have that ring, and that's that ring contracted into a clump. That ring started to spin faster and faster, and then we have our revolution, which means actually that farther into the past, the Earth's rotation was different. My understanding is it was spinning faster in the past, and it's slowly slowing down, just like a spinning top, because, there's not necessarily friction in space how we normally think of it, but the moon is tugging on the Earth, the sun is tugging on the Earth, the other planets are tugging on the Earth. So the rotation is not consistent over the lifetime of the planet. But we have the position that we're at now. Now, the cause of the tilt didn't look so much into the cause of the tilt, because our understanding is that the moon came from some kind of cataclysmic event where something crashed into the Earth and knocked off a chunk, and that became the moon. That could have added some tilt at that time. Suffice it to say, the planet Earth is slightly tilted in its orbit around the sun, and that tilt is what gives us our seasons. So I spoke about the evidence in the title. That's how at least one piece of evidence we have of the planet's tilt. So when we look at this illustration here, right now I'm in Austin, Texas. We're at the end of our summer. So what that will mean is that we're about and maybe my mouse is not showing up on the screen. Let me scroll this a little bit. If you look at this, we can see at the bottom it says summer solstice and autumnal equinox, September 21st. And thus we can see the planet is in between that area closer to the September position. And the reason why we have summer is because if you look at this top image on the left, when we're tilted towards the sun, the light rays from the sun hits us in a more direct angle, and thus there's more sunlight per area, and it's hot. When we look at the part where it says the autumn equinox, we're moving in our orbit around the sun. So the way the tilt is, and I'll show this more clearly on my pad here, the way the tilt is, as we spin around the sun, as we spin the whole way, like for instance, here in this part of the planet, we're not really tilted very, very much towards the sun or very, very much away from the sun. So we have a sort of average amount, right? So for instance, if the sun is here and we're tilted towards the sun, we see that, it gets pretty direct. If the sun was over here, then when I say over here, I mean here. Then as you can see at this point, the sun is sort of skimming off of us. We're not getting a lot of it. That's our winter. So basically in the winter or in the fall or spring solstice, we're sort of in the middle, and that's why we have sort of moderate weather in the autumn and the spring, right? Our tilt is such that going back to the book, is not really tilted so much towards, not tilted so much away, and we're in the middle between summer and winter. And Catherine says, why is it hotter in the summer in the southern hemisphere than the summer in the northern hemisphere? I'm not aware of that being the case, but if it's the case, we can look at the fact that the planet is simply not uniform. One of the things that actually impacts temperature is how much gets reflected and how much gets absorbed. They call that the albedo, right? So, for instance, if I have the Earth and it's cloudy, there's a whole bunch of clouds there, light will be reflected a lot. If I'm in Antarctica at the bottom of the sun, let me actually make sure the Discord is showing. If I'm at Antarctica at the bottom of the planet, there's a bunch of ice. It's white. So that would actually lend to it being cooler because more of the energy will be reflected, right? So if I was to pull up an actual image of the planet, and actually I pulled up my Himawari image for this reason, let's put it up and take a look and see what we have here. So I'll say and real-time Himawari. We'll show that. I'm going to move this up a little bit so it's easier to maneuver. There. And maybe I could expand the size of it a bit, right? So this is an actual live image from a Himawari satellite right here. So if we look at this, just even looking here, there's a whole lot of water here, right? We can see at the northern hemisphere, above the hemisphere, this looks to be America. No, maybe that's actually Asia. This looks to be Asia right here. That's a large landmass. To the left of that, we'll have Europe. We get to the other side, we have America, we have Canada. In the southern hemisphere, this looks to be Australia. We have southern Africa on the other side, but of course, Africa is pretty much on the equator. So just off my understanding, my general understanding, and looking in detail about that, looks to be a very different amount of landmass between the north and the southern hemisphere. So just from the fact that there's more landmass in the northern hemisphere, that will cause it to be hotter because when the sunlight comes, if it hits something that's reflecting the light a lot, bounces off back into space, is cooler. If that light is absorbed by the Earth, well, that's warmth that we'll feel. That's warmth that we'll feel. So that's part of it. But what I'll do is, that's actually another topic. That right there is, my general understanding of science. I want to make sure I address it, but that's another topic. So what I'll do is, in one of my future videos, I'll actually address that topic specifically. I'll look into it more specifically and give you a better answer. But based upon what I understand now, I would say that that's what's going on. It's simply the land masses is different, so we'll end up having a different albedo, and more heat will be absorbed and captured in the northern hemisphere than the southern hemisphere. It's such an understanding of how it works in general. You're welcome, Catherine. Glad I can help. But like I said, I'll still make sure and confirm the answer because sometimes things are counterintuitive. And maybe I'll find out something else. Or maybe I'll just find a confirmation and I'll come back and say, hey, I confirm that's the case and here's some more details about it. So we'll see to confirm. But one thing we can be sure of though, like even though the temperature may be different between, let's say the southern hemisphere is a little bit cooler in the summer. Let's say it's because more light is being reflected into the sun. We do know that when it's summer in the northern hemisphere, it's winter in the southern hemisphere. And of course, that's why. As we look at the image on the left where it says summer solstice, we're tilted towards the sun. But if you look at the southern hemisphere, like let's say where we can see South America, the light is more skewed when it hits that part. So basically looking at the image at the top, right from the sun, larger ground area, it's going to be cooler. And on the left where it's tilted toward the sun, it'll be warmer. So the fact that we have winter and summer at different periods on the northern and the southern hemisphere of the Earth shows that, or is one evidence of the fact that we have an Earth, that the Earth is tilting. Another interesting thing about the Earth's tilt is a lot of people may believe that the North Star that we have has always been the North Star, but it hasn't. Because just like a spinning top, how if you take a spinning top, and I used to love spinning tops when I was a kid, so that's why I like this analogy. But if we have a spinning top and it's spinning, if you spun a spinning top before, if you saw somebody spinning before, when it's spinning very quickly, it hooks up pretty well. But as it starts to slow down, you'll find that it starts to wobble, like it starts to tilt a bit, and the tilt spins itself. So let's say at one period of time in its spin, the tilt is facing that way, and very quickly, I mean, this is not a slow process, but then it goes that way, and the wobble is tilting. That the Earth is doing that. So if you look at the orbit of the planet, I'm going to go ahead and steal this Uranus orbit since it looks so nice. And I'll just copy it down. And now this is our planet Earth. Maybe I'll go ahead and throw a continent there. So that's a very badly drawn America, but you need to get the picture. So basically, this is wobbling too. So right now, Polaris is our pole star. But let's say, I believe, like 12,000 years from now, when it wobbles and the axis is here, it'll be something like Vega. At one point, it was Vega. So this axis actually goes around just like a spinning top, and over the course of about 25,000 years, we go around one cycle. So, and not to mention, of course, there's an even greater orbit with the rotation of the galaxy, but that takes, I don't remember off the top of my head, but it's like long, like many, many thousands of years. So hundreds of thousands of years probably. But that just means to say that the satellites that we have now, that we're getting like James Webb and stuff that could look extremely far into the universe. As a matter of fact, one of the classes I'm taking right now is an astronomy research class where we have to practically do some research in the class, and I'm learning some research methodologies and how research is done, and how to find the data we need out of the massive amount of data that we have. And I'll make sure I do a video about that. I'll make a note about that. North, south, temp, and well, I guess I'll have to focus on one of those. But suffice it to say, in our class on Thursday, the professor actually showed us some data from the JWST. Of course, so he's an astronomer, so he has a lot of data on hand. And he showed an image of the sky that this piece of sky is so small that he said if you take a penny and you hold it at arm's length, so you have a penny is at arm's length, and the eye of the head that's on the back of the penny, what is it? Abraham Lincoln, whoever it is, the eye of that figure, the eye of it now, on that penny held at arm's length, that's the area of sky that that picture was from, right? And when he zoomed that picture in that little piece of sky, there was like thousands of galaxies. Galaxies, not stars, galaxies. In that one little eye in the head on a penny held out at arm's length. It's amazing how many galaxies are out there. So I say that to say that maybe hundreds of thousands of years from now, well, not even maybe, I mean, in actuality, hundreds of thousands of years from now, when the Earth the whole solar system has revolved around the galaxy, if we point our telescope at the same orientation, we will see different galaxies because we've moved as a whole in the galaxy. So the different galaxies that at that same angle is different. It's pretty amazing. So there's many ways that we could study the same part of the sky at the same angle at different times, and not only see that the Earth is spinning, but we're going around the sun, and at a larger period of time, when we see the pole star change, that the Earth is wobbling, and in a larger period of time, we can see that the galaxy is moving because we can see a different part of the universe pointing our satellite in the same orientation as we did before. So yeah, some good stuff. So any questions or comments from anybody else in the chat? And I'll make this a short one just to give an idea of how the topics will go in the future. Talk about some interesting things in science and math and physics and you know, get some non-derp talk going on. Awesome. Glad you enjoy it, Larry. So interesting stuff. The universe is and that's one reason why I like astronomy. I mean, just the breadth of the universe and it's just amazing, you know. And of course, the first thing he mentioned this in class too, like one of the major topics in astronomy now, and I'm talking about mainstream astronomy. I mean, my professor, I mean, everybody at UT, I mean, it's a really, really good school, so they all like he's you know, has some good papers out. Matter of fact, part of our assignment that's coming up due was to look up his papers and see, you know, his popular papers, how many we could find that. There's databases with all of these papers and all the data. We can find papers, we can find authors, we can see how much they've been cited and so on and so forth. He has a lot of citations and you know, so he mentioned that now we're starting to look into, is there life out there? Because I mean, you can't look at an image that's the eye of the head of a penny held at arm's length and see thousands of galaxies and think, wow, can we really be the only life in the universe? Because you have to multiply. He gave me the number. I don't remember the number, but he did the calculation of, okay, given the area of this survey, how many galaxies must be out there? And it was like a lot, you know. So, and that's still just as far as we can see. That's still just as far as we can see. And they're telling it could be even more beyond that. I mean, how can we be the only life? Not even in the universe, but even in the galaxy. I mean, there's so many stars in the galaxy, but not even to mention a universe. How many galaxies how could we possibly be the only ones that life arose? So they're trying to look into that and see what are the probabilities and see if we can find life. Of course, now it's going to be mostly trying to find microbes and things like that, but the implication is clearly there, like finding intelligent life and maybe even life that's more intelligent. And then, of course, depending on who you talk to, some of them say they're already here or UFOs and things like that. I don't have any scientific evidence of that, but of course, I have my own observations and experience on that to discuss, but that's a different topic. But find it all very interesting as well. So awesome. So I'll be back next time, probably again on Saturday. You know, normally I stream on Saturday, but I had so much homework and stuff. This last week was the first week of school, and so I have like a full plate of classes, and I work as a learning assistant, and so I was helping with that a lot, and I'm also going to work as a student security coordinator as well. So very busy week. So I came on today while it was a slower day, and got the stream in, but everything's starting to level out. So I'll look for me again on this Saturday, and perhaps I'll look more into the temperature thing or more into some of the astronomical detailed things I'm learning in my astronomy class, which is still, I mean, it is still an upper level class, but I mean, it's you know, I don't have to like break out, you know, Wien's law, you know, just because. Let's talk about the fun stuff, and I keep it going. And Catherine says there must be more life out there with its own Goldilocks zone, like the Earth. It's fascinating. And before I go, let me actually speak about that a bit, Catherine, because I think it's easy to think that the Goldilocks zone is in itself. We as humanity, we always uh, uh, frame things from our perspective, which is understandable, right? I mean, the distance measurement that we utilize even when we talk about other stars and other galaxies or things like that. Well, I can't say other galaxies, other parts of this galaxy, I'll say for sure. I don't know if we found a planet in another galaxy, but I know that we know they're there. But we could actually see planets in our galaxy, like with the technology that we have. Um, we don't know exactly what life on another planet might be like. Like we know what our life is like because, of course, it's our life. But who's to say there's not another form of life that exists? Their Goldilocks zone is different. What we call Goldilocks zone is the temperature at which water is liquid, because we need liquid water to live. But I mean, who's to say there's not a different type of life that uses a different type of that's not necessarily carbon based? We don't know. It could be different. Who's to say that there's not a civilization that has technology that allowed them to live? Like there's people on Earth who live in places where uh, uh, water is not, liquid on the surface of the planet. Antarctica. We have stations in Antarctica where if you take water and put it outside, it's going to freeze, right? But we have the technology to make water be liquid by, having a building with a heater, right? So who's to say there's not a planet that's not in an area that we call Goldilocks that they maybe put a base there for whatever reason and have the technology to put it there. Or again, there could be a planet that we don't consider a Goldilocks zone, but is a type of entity that to them that's their Goldilocks zone. So I'm unlimited to that. Oh, it's a good point. Catherine said they could have evolved in methane and not be carbon based. Exactly. Right. So we don't know. Right. So even on Earth, there's microbes that live um, deep in the ocean where we wouldn't be able to survive. Or I guess I'm not sure about this, but I vaguely remember hearing something about microbes that live like in volcanoes or something like that. You know, so we don't know. But the fact is that we want to go to another solar system. The Goldilocks zone is important to us because if we go there and we find a planet that's not in that zone, well, we're going to have to bring a lot of technology or make a lot of technology there, and it's not convenient, right? But we shouldn't consider our Goldilocks zone the gold standard for life, period, because it could be very varied, just like it is on Earth. And so I will keep that in mind. So awesome. So thank y'all for joining. It's always good having people to talk to in the chat. Makes it more fun. And remember, respond, make a comment on this video, send me an email, join Discord. Let me know what science topics you want me to discuss, what map topics. And I'll try to come each week with a different topic, either expanding on the topic already discussed or a new topic. And remember, you can join Discord as well and talk live. You can talk live in the YouTube chat. I look forward to seeing y'all next time.